we can get started. So today we are going to talk about statistics and data analysis that will be used in this class. And this is part 1 because I just split the content of this lecture into 2 parts. So we are going to talk about the first 4 items today. I will save these outliers and linear regression for Thursday. So I just made some changes. So first today we are going to talk about significant figures. And then we are going to talk about errors, like how to quantify the errors. And then we are going to talk about the propagation of errors, especially the error propagation equation. And then we are going to talk about how to make comparison of the data with errors, because we always, like the data always have some errors, and this will be the t-test. So for the first one, which is significant figures. And here is the definition. So significant figures of a number in positional notation are digits in a number that are reliable and absolutely necessary to indicate the quantity of something. I think the definition itself is not important, but the rules of the significant figure are important. And here shows a example. So basically, for a number, we have some zeros in the front of other non-zero digits. So for these zeros, they do not count as significant figure. But for these ones, we also have some zeros like in between of the non-zero number. They count as significant digits. And for the zero at the end of the non-zero numbers, they also count. So in other words, for this one, we have 1, 2, 3, 4, 5. So it has 5 significant figures. And here are some more examples, or to be more specific, like non-zero digits are always significant. So this number has 4 significant digits. And any zeros between 2 significant digits that are significant or that are non-zero, they count as significant digits. So for this one, even though we have zeros in between, it has 6 significant figures. And for this one, for the zeros before the decimal point, they are not significant. Similarly, for the zeros after the decimal points and before the significant digit figures or the non-zero digits, they are not significant. So for this case, we have 0 at the very beginning, so it only has 3 significant figures. Similarly, for this one, we have 3 zeros at the very beginning, and they do not count. So both of these 2 numbers, they have 3 significant figures. But for zeros, after the significant figures or the non-zero digits, like the 0 here, it counts as significant digits. So for this one, it has 1, 2, 3, it has 4 significant digits. And last one, sometimes they will express the numbers in scientific notation. And in this case, we do not need to care about this one. We only need to care about the first part. And for this one, we follow the rules of this one. So for this one, it has 3 significant digits or 3 significant figures. So for this one, do you guys have any questions? No? Yes.
So if there is a if there's like a number that we have like 120, and we know it's exactly, we know that that 0 is like
120.
Yeah, and we know that that 0 is like actually measured. We didn't. Then how would we mark that it's significant?
Because this is after the non-zero digits, so we assume this is significant by default. So for this one, we have 3 significant.
Okay, and then what if we only knew like
we only know the first two.
Yeah.
Yeah, that's a good question. So we can use the scientific notation. So we can use this one to express. We only have two significant figures.
Okay. All right. Thanks.
So more questions? Nope. Okay. And the significant figures is important when we are reporting the data. And in this class, we are going to write homework. Or traditionally, we will have the lab reports. And we can see there are two examples from different groups of the previous students. We can see for the first one, it looks relatively clean and tidy. But for this one, we can see it's something is inconsistent here. We can see it only has one significant figure, but this one it has three. And I think we have something like even more. So this is not good. So when we are doing the homework, we need to take care of the significant figures and make sure they are consistent. But when we have the data for most of the situations, we will do some calculations based on our data. So it comes with the calculation with significant figures. And here I find a like government or regulatory document, which is from, I think from EPA. And here it provides some of the rules. So they are here. I'm not going to read the first one. You guys can take a look at it when I upload the slides. But here I want to focus on this too. So when adding or subtracting numbers with different degree of precision, which means with different significant figures, the answer should contain no digits farther to the right than the least precise number. And numbers should be rounded to one digit farther to the right than that of the least precise number. The answer is then rounded to the same number of significant figures as the least precise number. And this is a little bit confusing, but when we look at the examples, it will be more clear. And for the division and multiplication, the products or the quotient should contain no more significant figures than are contained in the number with the fewest significant figures. And this is a little bit more straightforward, but let's just say an example. So when we are doing addition, we can see this one has 4 significant figures, and this one it has 3 significant figures, but it doesn't matter. When we do the summation, we just calculate what we have. So this is the result. And in this case, for this one, it only has 1 digit after decimal point. It has 2 digits after decimal point. So when we are reporting the result, the sum can only has 1 digit after decimal point because it has 1 has 2. So we take the minimum. So this is 1. So we don't care about this part, but we are caring about the digits after decimal point. And this is the same for subtraction. It has 1 digit after decimal point. It has 2. So when we are reporting the result, it should only has 1 digit after decimal point. And so like they are the same. And for the multiplication and division, we take the least. So for this one, we care about the significant figures. For this one, we have 4. For this one, we have 3. And when we report the result, so this is the product. When we report the result, it should have 3 significant digits because 3 is smaller than 4. So we need to round this result to 3 digits. And similarly for the division, this one has 4, this one has 3, and we can get the result here, but we need to round it. We need to round it to 3 significant digits. So this is the rule. So for this one, do you guys have any questions? And like the previous student has a question, like sometimes when we have the data like the count, like 1, 2, 3, 4, 5. So for this one, I would say we can assume that the count number is infinitely precise. So even though we have like 4 times 1 and this 1 refers to the count, we did not care about it. We just report the significant figure of this one. So the result will still be this one. But in my experience, I haven't used the count as the input data of my research. But so I think this is not quite common. So when we are doing the homework, we may also need to work with tables like with the Excel, Word, probably no PowerPoint. And here I just make the demonstration to just demonstrate these things. So if you are not quite familiar with working with data between Word and Excel, you may take a look at this. And here's a so next, we are going to talk about the errors. Here's the definition. So the error or the full name is measurement error, and it refers to the measured quantity value minus a reference quantity value. And here I use reference quantity value, but we can understand it like the true value. But in reality, the true value, like we do not know the true value. So we may just pretend or we make the solution or something to say that we know its real concentration, and then we just use the instrument to remeasure it, and then we do the comparison. And under this situation, we call this as a reference value. And for the uncertainty, and the full name is uncertainty of measurement, it refers to the non-negative parameter that can characterize the dispersion of the quantity values being attributed to a measurement and based on the information used. So I think this is a little bit abstract, but I would say, so the error refers to a quantity, and then uncertainty refers to a groups of errors or the bulk of the error, and it refers to the parameter that can describe, like if we put all of the errors together. But I think in practice, sometimes we may just say error or uncertainty interchangeably. So, but I think it's good to know they have a little bit difference. So for this one, do you guys have any questions?
I have a question from the previous slide.
This one,
I know.
this one.
Yeah. So for the multiplication, we did 1.43. We assume that's 3 significant, and 113.2 we assume 4 significant, right?
You mean this one?
Yeah. Yeah. Do we change the definition within the addition? Because in addition we had the 113 be only 1 significant.
This one, 113.
Yeah, that's probably where we're doing addition.
This one,
Yeah.
it has 4 significant figures.
Oh, so maybe I got confused.
Oh,
1 and 2.
1 and 2 refers to the digits after decimal point,
Okay.
and here refers to the significant figure. Yeah, like for the addition and the subtraction, we care about the digits after decimal point, but for the multiplication and division, we care about the significant figure.
So that 1 and 2 are not the significant figures, but rather just the
digits
the
after
digits after
decimal
the
point.
decimal.
Yes. Okay, then we are going to talk about the source of errors. And traditionally, we will be talking about these 3 classical source of errors. The first one is observer, and we know that different people has different feelings. Like if they ask the people to identify the color or like to recognize the scale, like to do some estimation, different people may have different results. So it may come from the observer. Also, it may come from the methods of measurement. For example, if you are doing some measurement based on color change, and the color change is due to chemical reaction, but this chemical reaction may not be complete. For example, we may only have 99% of the reaction. So we may introduce some of the errors. It may also come from the instrument itself. So like the measurements may be out of range, or the instruments or may not be zeroed. And another one I want to talk about is object to measured. Like whenever I was preparing for the material, and some of the literature, they talk about the object to be measured. This could be due to the heterogeneity of the objects, or the edge may not be well defined. For example, here shows the concentration of DDT in the field, and we can see it has different concentrations at different places. I can make this larger. So suppose we want to know the average concentration of DDT in this area. So ideally, we can take infinite number of soil samples from this area, and then we measure the concentration of every sample, and then we calculate the average. But in practice, this is impractical because we cannot take so many samples. So in practice, we may just take several samples at different places. And we can imagine that by taking different samples, like every time we may get different results. So in other words, we can never get the true average concentration of DDT in this field. So basically, this is due to the heterogeneity of this object itself. So for this one, do you have any questions? Yes.
Could you explain how the
Yes, methods. So just an example. For example, we are going to measure the concentration of some chemical, and this reaction is how to say. For example, we are going to measure the concentration of some chemical in this solution, and then we want to measure its color. And so basically, when we add some of the reactants, and when we add this chemical into the solution, the color will change to, let's say, change to blue, and the blue color is better than the transparent solution. And this color change is based on the chemical reaction. But as we mentioned in the last lecture, the chemical reaction may not be complete. So like if we wait 1 hour, it can be 90% complete. If we wait 4 hours, it can be 99% complete. And if we, let's say, 100 hours, it could be 99%, 99% complete. We know as the reaction goes, the rate will go down. But in practice, we may not be able to wait 100 hours. We may only wait for 4 hours. And in this case, the reaction is not complete. So we cannot get the true result. And in this case, we will introduce some of the errors. So any more questions? The next slide is about the types of error. So the first one is random error. So because when we are doing the measurements, anything will be influenced by the environment or by the nature, and they are random. And so in this case, the data are usually scattered approximately or symmetrically about a mean value. It will affect precision. I will talk about precision in the next slide. But generally, we can deal with this statistically, which means because for the random error, the average of the random error usually equals to 0. So we can take many samples or take many measurements and then take the average. In this case, in this way, we can minimize or cancel out the random errors. And the next one is systematic error. So it refers to the readings are too high or too low, and it will affect accuracy. Again, I will talk about accuracy in the next slide. So in this case, if we assume this part is like accurate or almost no error, and the random error refers to this case, we can see the points are scattered around the true value. And for the systematic error, it refers to like the data are like shift or get like totally get away from the true value. And we also have another type of error, which is a gross error. And this is usually obvious, and when we consider it as outlier, and it can be detected by carrying out sufficient replicates of measurements. If we only have one measurement, we cannot identify the outlier.
So like, what would gross error, sorry, what would gross error look like? If, I guess we're using like the bullseye example.
It will be something like here, like if still the target is here, but the gross errors are something like
Oh, wow, okay.
yes. Or to be more specific, like they may have some data like this, but for the gross error, it will be one data. I will talk more about this in Thursday's lecture. Any more questions? Let's look at accuracy and precision. So accuracy refers to the measurement of agreement between measured value and the true value. And again, the true value is usually unknown, or we may call it as a reference value. And we will be talking about the reference value in the organic chemistry units. And I guess at that time you may have more understanding about this reference value. And so we can have some quantities to quantify the accuracy. Sometimes we may use the absolute error, which we just use the measured value to minus the reference value or the true value. And we may also use like the relative error, which is like, so this is the absolute error. We use the absolute error divided by the true value or the reference value and times 100%. So this is the relative error. So geometrically, accuracy refers to the distance between our measured data and the true value. And we can see that we want to have the data with small precision so that our measurement data will be closer to the true value. So basically, the accuracy, the smaller is better. And, the next one is precision. Yes, another page. So precision relates to the reproducibility of the results. Or in other words, it shows how similar the values obtained in the same way. So we want to make sure when we are measuring the same objects, the results are the same or similar all the time. And so in this case, if this refers to the data that we are measured, and precision refers to the scatteredness of our data. And we can have some quantities to quantify the precision. And the first one is absolute difference. And the definition is like this. So here should be X bar. I guess there should be. So we use our measurements minus the average. So in this case, we do not use the true value. It has nothing to do with the true value. We use our measurements minus the sample mean, and then we just take the average. But more frequently, we are using the standard deviation, or the full name is standard deviation of sample. And the formula of or sample standard deviation is like this. And again, they just kind of calculate the average of this square of their difference. But note that this is -1 instead of n. So I think when we are learning, like when we are taking the statistics class, like when I was young, I was confused why here is a -1 instead of n. But similarly, we also have another parameter of statistics, which, so this is sample standard deviation, and we also have the population standard deviation, and we usually use sigma to note this, and this is a -1, and then we make the summation of xi minus x bar squared. So for the population standard deviation, this is n, but for the sample standard deviation, this is n-1. And in most of the cases, because we cannot measure every sample of our population, so for almost every situation, we use n-1 instead of n. So for this one, do you guys have any questions? So here's a summary. So they have precision and accuracy, and they have low and high. So in general, we have these 4 combinations. And the first one is the low accuracy and the low precision, which we do not like. And ideally, we can have the results with high accuracy and high precision. But because this is perfect, so we are trying to chasing it, but usually they cannot get it. And so in practice, we usually have these 2 combinations, like that they are more reasonable or practical, which is high accuracy, but the precision is low, or the low accuracy with high precision. So between these 2 options, do you guys think which one is preferred? Or which one do you guys prefer? Which one? High precision with low accuracy. How about other?
I would say high accuracy, low precision.
Still this one? This one? Why?
Because I mean, in terms of like gathering data, I rather want to be like accurate. I guess rather than being like not having accuracy, but then like but having like constantly getting like the wrong information.
How about Amir? How do you, why do you prefer this?
Prefer that one because as long as you're precise, you can always calculate our bias.
Like you can calculate.
Yeah, exactly. You can know how far we are off from the true reality, but our data is precise at least. Whereas where it's not precise, it's all over the place. Sometimes you really don't know where the true value is, so it might be really off, and then it's also we have an error, a larger error for our bias.
How about others? Do you, any of you? Let me check. They have. Okay, so I would say this is reasonable, but I would say this one is preferred. The reason I would say because we can just simply take more samples and then we can get the true value. But for this one, if we need to, as Amir said, we need to calculate this bias. But this bias may not be easy to calculate. I mean, this is also a good choice, but this one is, I would say, more simple because we can just increase the sample size. So I would say this one is preferred, but this one is also used. Yes. So for this one, do you guys have more questions? So in the lab, we have like the instruments, and for any of the instruments, we will have the accuracy or something like the precision, and this is for the pipette. And we can find this on the menu, and this is for the volumetric flag. And again, it has this is called tolerance, but in general, this is the absolute error. And we also have the scale. And in the teaching lab, we have two types of scales. And for each type of scale, they have different absolute error. Yes.
Which one is which?
Yes, that's a good question. This one is this one, and this one is. So the one has the shield to prevent the wind, which means this is very sensitive. So this one is the more accurate. But in homework, we are going to do some of the calculations based on the measurement error. And here at the end of the homework, we have this appendix. So we just provided the absolute errors of each of the instruments. So when we are doing the calculation, we can just refer to this table. Any more questions? And the next one is about the propagation of errors. Like when we are getting some of the measurements, we may not use this result directly. For example, we are interested in the concentration, but we need to use the mass divided by the volume. So the mass and volume will be measured separately. Although we may say the concentration nowadays, the concentration of some chemical can be measured directly, like by TC or ICP. But sometime in the lab, we are going to use these two values. And here I just show an example of some functional relations. For example, we have the concentration equals to the mass divided by volume. Let's just focus on the concentration and volume. We can see that so the concentration is a function of volume. And we can see this relation is not linear. So suppose we have a measured data which is at 0, we can consider it as the volume. And when we are doing the measurement, it has the measurement error delta x, and we can see it is symmetric around x0. But when we are doing the projection or the functional transformation, because this is non-linear, so when we are doing the projection, this one will project it to here, and this one will project it to here. We can see that delta y1 does not equals to delta y2 because this is non-linear transformation. And in this case, this will be a little bit complicated because if they are not equal, then we have to use some other techniques to express this uncertainty, which is very inconvenient. So in practice, we can assume delta x is small. And in other words, we can assume the measurement error of our instrument is very small, or they are relatively small. And by assuming delta x are small, then we can use this straight line to approximate this curve at this point. In this case, when we are doing a projection based on this straight line, we can see that delta y1 and delta y2, they are equal, and we can just say they equals to delta y. And in this case, they are symmetric and equals to each other. And based on the calculus or the geometrical relations, we can see that delta y equals to the slope of this curve at this point, at the slope of this straight line, times delta x, which is the error of this x. So you guys do not need to do the calculation based on this. I just want to show the origin of error propagations. And but in practice, as we can see, the m or the mass, it is also a variable. So generally, we have this y has different input variables, like the v or c, and blah blah blah. So we can have this form based on the multi-variable function, and then we can just go through some of the process. And we do not, like if you are interested, you can take a look at this. And these are based on the paper shown here. But you do not have to know how did they come. But finally, we will have this result. And the result is delta y squared equals to the sum of this parts and then times the square. So we can see this is the slope of xi, and this is delta xi. And then we take the square and make the summation. Again, we do not have to use this to do the calculation, but I just want to show this one. Here are some examples. And in environmental chemistry or in this class, we are going to do some summation or subtraction. Like we have a total volume and it's equals to V1 plus V2. Like we are going to dilute some of solution when we use like this summation. And we can see, and the general form of summation or subtraction is here. Like if A1 is negative, then it is a subtraction. Again, I'm not going to show the whole process, but finally, we can have this result. So this means delta y, like the arrow, the square of the arrow of the sum equals to the square of each part. And so for division, which we also frequently use, like the concentration equals to the mass divided by the volume. So the general form is like this. And again, we are not going to talk about how to derive that, but here the result. This result shows that the relative error of y, then we take the square, equals to the square of like sum of the square of its relative error of each component. So it has this form. Similarly, we have this multiplication. For the multiplication, we can also do some calculation and we get the result here. And surprisingly, we can see that they're the same. So even though this is division and this is multiplication and they follow different process to do the calculation, but the results are the same. So when I first look at this, I like this. But when I do the whole process by myself, I find that this is natural. But here there's a summarize of the error propagation equations that may will be used in the homework or in our research. So at first, I would like to talk about this Pythagoras theory, which I think everyone are familiar with. Like if we have this triangle, and we can see the square of C equals to the square of A plus the square of B. And similarly, for the summation, like y equals to x1 plus x2, or y equals to x1 minus x2. Again, we can draw this triangle, and I call this triangle of absolute errors. And we can see this is delta x1, this is delta x2, and this is delta y, which is a sum. And based on this triangle, we can have this relation. So similar to this one. And for the multiplication and division, we have this form. Similarly, we can make the triangle of relative errors because they are based on the relative error. And based on definition, we can see this is the relative error of first component. This is a relative error of the second component. And this is a relative error of the result. Again, we can, based on this triangle, we can write down this relation. So this is the error propagation for summation and subtraction. And this is the error propagation equation for division and multiplication. So basically, we can find these equations online or on the paper or on the slides, but it will be faster to solve problem if we can remember it. like we can. Yes. So for this one, do you guys have any questions? No? Okay, and here shows any. Oh, so here, so all of the things that I talked about before about error propagation equation are based on this paper. So if you are interested, you may take a look at this paper. And this paper also summarized the error propagations of different forms. And we can see it has some weird form that I never seen, but maybe in future, if you want to use the error propagation equation, you can just take a look at this table. And all of these equations are derived from the partial differential equation that we talked before. So we have the error propagation equation, and here is an example. So let's say you are diluting a wastewater sample for further analysis. And at first, you add 10 ml plus 0.02 ml wastewater sample into a beaker. And then you add another 25 ml DI water into the beaker because you want to dilute the wastewater sample. And here are the questions. First, so that should be it. What is the absolute error and relative error of the mixture? So in this case, we have like V1 equals to 10 plus this one, and we have V2 equals to plus minus 0.3 mil. In this case, first, we can calculate the total volume without error, which is 10 plus 22, and we have 33 mil. And then we can use the error triangle to calculate the absolute error of this summation. In this case, this is 0.02, this is 0.03. I guess this should be 3, this should be 2 because definitely is larger. But the concept are the same. And then we can calculate the length of this side, which we have this equation. And we can solve this equation. And this is the absolute error of the total volume. And then we can calculate the relative error because we know the value of this V here, and we know the value of this delta V here. So we can do the calculation, and here is the relative error of the total volume. So for this example, do you guys have any questions? No. And here we can also see that no, just this one. And then let's look at the second question. Now you plan to add 5 milligrams of NaCl into this mixture, and the measurement error of the balance is 0.1 milligram. And the question is, what is the absolute error and relative error of this Na, like sodium chloride solution, or the concentration of this sodium chloride? So in this case, we have the concentration equals to the mass divided by the total volume. So first, we can calculate the concentration of this sodium hydroxide. So C equals to the M. M is known, which is 5, and the V is also known, is 35. So we can just plug the number into this equation, and we can get this result. And usually the concentration are expressed as milligram per liter. So we just convert this milliliter to liter. And then we want to calculate the relative error of NaCl. And because this is the deviation, we can use the triangle of relative error. So in this case, we have this relation. And in this equation, delta M is here. So delta M is known, M is here. So the M is also known. and the relative error of the volume has been calculated here. So in this equation, all of them on the right side are known. So we can calculate the value of the left side, which is here. Note that we just take off this square. So the relative error is 2%. And then we can calculate the absolute error, which we just use 2% times the value of C. And the result is this. So for this one, you guys have it. Or if you have questions, yes.
So for the C value on the bottom, where the 1.13 times 10 to the negative 4 come from?
Oh, it should be this one. Oh, I guess
Oh.
there's a typo.
Okay.
Yeah, I'm
thank you.
sorry. There should be 4.3. Yeah, you can double check if this result is based on this value. Any more questions? Yes.
How do you know when to do the division for the relative error and when to do the other one?
When do the division of which?
Yeah, for the second question, how you do the division? Yeah,
Oh, yes, because this is a concentration. So first, we can list the equation to calculate the concentration. And we know that this is division.
gotcha. Okay.
Yes. Any more questions? No? I guess we still have one, which is t-test. I guess I will save this for Thursday, and I will adjust the slide a little bit. So on Thursday, we are going to talk about the t-test. And if you guys are interested, you can take a look. But here we can just use the rest of time to just summarize what we have done for the first 3 items. So first one, when we are reporting the data, I need to pay attention to what? Significant figures? Yes. In environmental science, the significant figures are usually, which I didn't talk about. This is usually 3. Because if we have 3 significant figures, so even though this is +1 or -1, we will have like 1% difference. So this is considered to be small enough. And the next one, source of errors includes which of the 4? Observer. And instruments. And the last one is yes, the object to be measured. And for the types of error, it includes random, systematic, and gross error. And here, because we talk about the triangle, so so we can just write down this by ourselves, but note that this is delta by, that's delta by square. And finally, just note that on Wednesday, we are going to have the flint. We are going to prepare the flint kits, like for the take-home experiments. And also note that assignment 1 and quiz 0 and quiz 1 will be due on next week. And that's it.